Hello everyone. Today we'll discuss on this sequence impedance of the symmetrical circuit. As we have seen in earlier classes and all, we have seen that there are means about sequence voltages, sequence currents. Okay, as you know, sequence currents and sequence voltages are of positive sequence, negative sequence, and zero sequence. Similarly, today we are going to deal with sequence impedances. Okay, of a symmetrical system. Let's see the introduction before going to take a derivation of this. Let's define a positive sequence impedance, negative sequence impedance, and zero sequence impedance. Okay, let's define. As we know the impedance definition, in a similar way we are going to define this one with respect to a sequence wise. Okay, let's see first one. The impedance offered by the circuit for the flow of positive sequence current is called as a positive sequence impedance. Okay, similarly, the impedance offered by the circuit for the flow of negative sequence is called as negative sequence impedance. And then the impedance offered by the circuit for the flow of zero sequence current is called as zero sequence impedance. Okay, now we got all three definitions. Let's derive this one. To derive sequence impedances for a symmetrical circuit, so let's consider a circuit which consists of three phase, that is A, B, C. Okay, along with the neutral. Okay, as shown in the figure. Right, let's define this voltage across voltage across this, that is VA, first phase voltage across this, VB voltage at VC. Okay, it means define VA, VB, and VC. Let's see how it comes. The voltage drop can be calculated as a VA is equal to, okay, VA is equal to, just observe in a circuit, VA is equal to IA into ZA, complete the circuit, so IA into Z plus IN into Zn, okay, in this circuit, right? So in that way, if you are expressing VA is equal to IA into Z plus IN into Zn, right, IN into Zn, right, IN into Zn. So in this way we can define this VA equal to IA into Z plus IN into Zn. Let's take this one, IA into Z, express this IN as IA plus IB plus IC, because as you know in this IN is equal to IA plus IB plus IC. Okay, so next substitute that one, IN as a IA plus IB plus IC, and then expand this one. If we expand that, IA plus IZ, see IAZA, okay, and then here it comes your IA plus IB plus IC. So now what we can take is IAZ plus I, expand this equation, IAZ plus IN, ZNIA plus ZNIB plus ZNIC. So once we expand this equation, take terms like IA, IB, IC separately. So now first you make this. So when you expand this one, IAZ plus Zn into IA. So among this, take a IA outside, Z plus Zn you can write. Similarly, you express VA in terms of this one, IA, IB, IC along with the Z, right? First one is VA equal to Z plus Zn into IA plus Zn into IB plus Zn into IC when you are calculating VA. Similarly, VB can be calculated by applying the same formula, means in a similar formula. Okay, VB is equal to, if you simplify again in this way, you will get VB is equal to Zn IA plus Z plus Zn IB plus Zn into IC. Okay. Similarly, your VC also can be calculated Zn into IA plus Zn IB plus Z plus Zn IC. Okay. So consider, means all three equations, VA, VB, VC, 1, 2, 3 equations you can say. Let's write these three equations in a matrix form. Okay, let's write these three in a matrix form, that is VA, VB, VC as a column matrix, and then this equations can be written as IA, IB, IC. You can write in terms of IA, IB, IC. So when you write IA, IB, IC, take VA is equal to Z plus Zn, Zn, those values you can write. I hope you know how to write this in equation, means matrix form, or write in a similar way, right? Once you write, let's express voltages, that is VA, VB, VC and IA, IB, IC in terms of sequence components. Okay, that is, as you know, VA, VB, VC is equal to 1 1 1 1 A square A 1 A square into VA naught, VA1, VA2. What do you mean by VA naught? It is a zero sequence, VA1 is a positive sequence, VA2 is a negative sequence. In a similar way, you have to express IA, IB, IC, that we can express in the same way, that is 1 1 1 1 A square A 1 A square, IA naught, IA1, IA2. Okay, in this way, right? Let's substitute these two equations in above equation. That is in this equation, VAB BVC is equal to Z matrix into IIB IC. Okay, so once you substitute, VA VB VC is nothing but your 1 1 1 1 A square A 1 A square, VA naught, VA1, VA2. Alright, now we need to express VA naught, VA1, VA2 is equal to what? Okay, and then we have to get what is the impedance equation. Okay, in the form of sequence components, right? So what we can do is, let's send this one VA naught, VA1, VA2 as it is. Send this matrix this side. Okay, your right hand side. When you send that, it comes 1 1 1 1 A square A 1 A squares inverse matrix. Okay, and remaining terms as it is, right? As you know, we have already done this one previously. To find the matrix inverse for this particular matrix, inverse will be 1 by 3 I 1 1 1 1 A square 1 A square A. Okay, just substitute in the place of 1 1 this matrix inverse, just substitute in the place of this 1 by 3 of this matrix. Okay, let's see. Therefore, VA naught, VA1, VA2 will be equal to 1 by 3. Just this matrix inverse we have substituting here. And then next further terms are as it is. Okay, on simplifying these equations, okay, entire multiplication of this 1 1 1 1 A square 1 A square A matrix into Z plus Zn 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 sorry Z plus Zn Zn and this matrix along with 1 1 1 1 A square A 1 A square. These three matrix, if you simplify multiplication, if you multiply all three matrices, you get Z plus 3Zn 0 0 first row, and second row is 0 Z 0, and third row is 0 0 Z. Okay, so this, how to get this one, I have solved already, and I'm going to upload it as a PDF along with this video. Okay, so when you solve this, you get VA naught, VA1, VA2, that is negative sequence voltage, positive sequence voltage, and a negative sequence voltage will be equal to this form, this matrix into IA naught, IA1, IA2. If you simplify, that means from that equation, from this last equation, okay, last equation, we can write that VA naught equal to Z plus 3Zn into IA naught, VA1 equal to Z into IA1, VA2 equal to Z into IA2. Okay, so therefore sequence impedances are defined as Z naught will be defined as VA naught divided by IA naught. Okay, voltage divided by current of that sequence itself. That is nothing but your Z plus 3Zn as from this above equation. Okay, that is nothing but your zero sequence impedance, and positive sequence impedances VA. From this second equation we can write Z is equal to VA1 divided by IA1. Okay, VA1 divided by IA1, which is equal to Z, what you have got, right? This is your positive sequence impedance. Similarly, Z2, that is the negative sequence impedance, will be nothing but your VA2 divided by IA2. Okay, so VA2 divided by IA2, which is equal to Z. This is your negative sequence impedance, right? So from this above equations, what we can conclude is that for a symmetrical static circuit, like transformers or fully transposed transmission lines, remember this. Okay, we can define, means we can give a conclusion for 2 points. First one is the positive sequence impedance is the same as that of negative sequence impedance, and the second one is zero sequence impedance is much larger than the positive or negative sequence impedance. Okay, in the absence of neutral, Zn will be equal to infinity. Okay, therefore Z0 is also equal to 0, infinity. Z0 is equal to infinity. Therefore what we can define is Ia0, that is negative sequence current, will be equal to Va0 divided by Z0, right? Va0 divided by Z0 is infinity. If you substitute that, we get a 0. That's what earlier numericals as well as in earlier derivations we have come across this, right? Ia0 equal to 0, right? As we have seen it. Note one point, that in this case, means in the symmetrical components or symmetrical impedance of a symmetrical circuit, for this particular circuit, even if the elements are mutually coupled, okay, if the elements are mutually coupled, it can be proved that the sequence impedances are uncoupled provided the circuit is symmetrical. Okay, even though if you have a mutual coupling, then also we can define the same thing, right? So only one thing is that circuit should be of a symmetrical one, right? Thank you.